Acids and bases, high level 5. pH curves, buffer solutions. What is a buffer solution? Well, buffers are solutions that resist changes in pH when small amounts of acid or base are added. The pH of blood must be maintained between 7.35 to 7.45. Change of only 0.2 to 0.4 pH units is fatal. And you can see this bicarbonate to carbonate equilibrium is maintained in the blood, and this is the buffer used by us humans. Application 2. Several chemical equilibria buffer systems help maintain the pH of seawater at around 8. This is essential in helping to maintain coral reefs. Buffer solutions are made to control the pH at a desired value, and acidic buffer solutions contain high concentrations of a weak acid and its salt, containing the conjugate base. For example, a weak acid, ethanoic acid, and its salt, sodium ethanoate, would be present in a buffer solution. Basic buffer solutions contain high concentrations of a weak base and its salt, containing the conjugate acid. So there'd be a high concentration of the weak base, ammonia, and a high concentration of the salt, ammonium chloride, and obviously some of the conjugate acid would be present. Consider this general acidic buffer system made by mixing HA with its salt, NaA. The equation for the buffer is the same as the dissociation equation for the weak acid. You can see here we're adding some weak acid molecules and weak base, the anions, and you get a mixture of them in solution. There's the weak acid present and a lot of the weak base present. So a high concentration of HA and a high concentration of the ion, or the anion. So high concentrations of both of these species help maintain the H+, the concentration of hydrogen ions. Let's consider how the pH of the system is calculated. Well, we've got this basic equation here. We've got the molecule undissociated and its dissociated ions in equilibrium. So the equilibrium constant is the products, the concentration of the products over the concentration of the reactant. If we rearrange it, we can see, given that this is a constant at a particular temperature, that the concentration of the hydrogen ions and consequently the pH of the system is to do with the ratio of the molecule and the anion. As long as this ratio remains the same, or very close to it, the concentration of hydrogen ions will remain the same. What happens when small amounts of acid are added to an acidic buffer? Well, remember, we've got a high concentration of the molecule and a high concentration of the anion. If we add H+, the A-, the anion, reacts to use up the added H+, as shown below. Haha. So we're losing a little bit of this and making a little bit of this. But since there are large amounts of A- and HA at the start and small amounts of H+ added, there is little change in HA and A-. If you look at this table here, before the reaction, if I've got a concentration of 10,000 for HA and 10,000 for A-, we'd have a ratio of 1. If we were to, let's see what I say, adding 10 H+, at the very most, we'd then get 10 more of these. So you'd get 10,010. And here you would get 9,900. And so you just have 10,010 divided by 9,900, which is still roughly 1. So there'd be very little change in the ratio, and so consequently very little change in the concentration of hydrogen ions, so very little change in the pH. What will happen when small amounts of base are added to an acidic buffer? So let's add some OH- to our equilibrium, and this time the molecule HA will react to use up the added hydroxide ions. Here we can see it go on, make some water and some more anions. So some of this is being used up and some of this is being made, but they're already massively in excess of this. So since there are large amounts of HA and A minus at the start and small amounts of a hydroxide ion added, there is little change in the concentrations of HA and A minus. So this time we are losing 10 of these, so we'd have 9,990 roughly here, and we'd have 10,010 concentration here. And so the ratio once again is going to be very close to 1. There'll be almost no change in the concentration of the hydrogen ions, and consequently very little change into the pH. We have buffered the solution. What happens when small amounts of acid or base are added to a basic buffer? Well, let's have a look at ammonia with the ammonium ion and the hydroxide ion. If we add OH minus, the NH4 reacts to use up the OH minus. That's like so. If the ammonia reacts to use up, if we add H plus, sorry, then ammonia will react to use up the H plus with the following equation. And since there are large amounts of ammonia and the ammonium ion at the start and small amounts of the hydrogen ion or hydroxide ion added, there's little change to the concentration of ammonia and the ammonium ion. So the concentration of hydroxide is not changed, and so the pH once again remains the same. Preparing buffer solutions. There are a few methods of doing this. Let's look at the first method. We can mix weak acid or base with its salt. For example, you can mix solutions of weak acid or base and salt together. If you had 50 centimeter cubed of 0.25 mole ethanoic acid and 100 centimeter cubed of 0.25 moles sodium ethanoate, you'd have a buffer solution. You can see here we're using twice as much of the sodium ethanoate as we were of the ethanoic acid. Example 2. Add solid salt to a weak acid solution. We've got 50 centimeter cubed, 0.25 mole ethanoic acid and 5 grams of the sodium ethanoate of the salt. Another way of doing it, you can add solid salt to a weak base solution, 200 centimeter cubed of 0.4 mole ammonia and 5 grams of the solid ammonium chloride. So a few very straightforward methods there. Another solution, add a strong base to a weak acid to half neutralize the acid, and that's the important bit. You want to only half neutralize it. The neutralization reaction produces a salt, A minus. The buffer equation would be the molecule, HA, dissociating into the hydrogen ion and the anion. So you have the acid and salt acting as buffers in the neutralization reaction, which is as follows. So the acid, weak acid, reacts with a strong base to give us a lot of these anions because it's forming the salt, and so we have lots of this acid and lots of this salt present. You add enough sodium hydroxide to neutralize half of the acid because you do still want some of the acid left. So acid plus the salt is the buffer, and you've got the anions and the molecules of acid in solution, in the buffer solution. Method 2A. Add a strong base to a weak acid to half neutralize the acid. Here's the buffer equation. We've got ethanoic acid with the ethanoate ion and obviously some hydrogen ion present. If we add 25 centimeters cubed of 0.1 molar sodium hydroxide, the strong base, to 50 centimeters cubed, 0.1 molar ethanoic acid, you can see straight away that we're using half the amount, because these have the same molarity, we're using half the amount of sodium hydroxide as we are ethanoic acid. So the initial moles of ethanoic acid, we can just use C times V. We've got 0.1 moles of 0.05 decimeter cubes to find how many moles we've got of the sodium hydroxide, of the ethanoic acid, sorry. The moles of sodium hydroxide acid added 0.1 times, and so we've got 25 centimeters cubed, so 0.025 decimeter cubed, to give us 0.0025 moles. Therefore, the moles of ethanoic acid left, if we had 0.005 moles to start with, and it's reacting with 0.0025, would have 0.005 minus 0.0025 to give us 0.0025 moles remaining. And if 0.0025 moles are reacting to form this, then we're going to get 0.0025 moles of the ethanoic ion forming. This is a buffer solution. Both the weak acid and its salt, the conjugate acid, are present in high quantities. Let's have another look. Adding a strong base to a weak acid to half neutralise the acid. Buffer equation. You've got the ethanoic acid and you've got the ethanoic ion. But look here, we've got 50 centimeter cubed, 0.1 mole decimeter cubed of the strong base, sodium hydroxide, and 50 centimeter cubed of 0.1 moles per decimeter cubed of ethanoic acid. Can you guess what's going to happen here? Are we going to get a buffer solution? Well, they are the same. So the initial moles of ethanoic acid would be the concentration multiplied by the volume, which gives us 0.005 moles. And we're adding 0.1, we're adding the same amount of moles of sodium hydroxide. And so the moles of the ethanoic acid left, once you reacted, would be 0. There'd be no acid around to neutralise the addition of hydroxides. And so, not a buffer solution. You need to have some acid present to mop up hydroxide ions. So this would be no good at all. 2b, add a strong acid to a weak base to half neutralise the base. The neutralisation reaction produces the salt of the weak base. So the buffer equation, ammonia with water, giving us the ammonium ion and hydroxide ion. And the neutralisation reaction is ammonia with the strong acid, hydrochloric acid, to give us the ammonium ion, the chloride ion. We've got 25 centimeter cubed of 0.1 molar HCl, and 25 and 50 centimeter cubed, twice the amount of 0.1 molar of the weak base ammonia. The initial moles of ammonia, we use concentration times volume. Just plug them in, make sure you change centimeters cubed to decimeter cubed. So now we know the moles of ammonia. And then the moles of hydrochloric acid added. We've got 0.1 moles of 20.025 decimeter cubed. So we've got 0.0025 moles of the strong acid and 0.005 moles of the weak base. You react them together. Half of the NH3 will react, and so half will remain. And the moles of NH4 formed will obviously be the amount they reacted, which is 0.0025. So we're going to get 0.0025 moles of the ion forming. So we will have a buffer solution because both the base and its conjugate acid are present. Acidic buffers obviously have a pH below 7, and they're formed from a weak acid and its salt. For example, ethanoic acid and sodium ethanoate. The buffer equation is just the equation for the dissociation of the weak acid. And so in this case, it would just be the ethanoic acid and the ethanoate ion, which is present in the salt. Basic buffers have a pH of above 7, and it's a weak base in its salt. For example, ammonia, ammonium chloride. The buffer equation is just the equation for the dissociation of the weak base. So NH3, NH3 reacting with water to give us the ammonium ion and hydroxide ion. You'll notice these two warnings here. It's not common for people to get a bit confused and write buffer equations as the acid reacting with the salt, which of course is nonsense, much as the base reacting with the salt would also be nonsense in the case of these buffers. Okay, I'd like you to press pause and write the equation for these buffer systems. Right, question 1. The equation for the buffer prepared by mixing benzoic acid with sodium benzoate. Well, what we need to do is find the acid and write the dissociation of it. So we've got the acid dissociating into its anion and hydrogen ion. Next, write the equation for the buffer prepared by mixing methylamine with its salt, methyl ammonium chloride. So we're just looking for the dissociation of the base. So reacts with water, take us the hydroxide ion and the cation. 3. Write the equation for the buffer prepared by mixing solutions of sodium hydrogen carbonate and sodium carbonate. Hydrogen carbonate ions are weakly acidic and their conjugate base is the carbonate ion. So it's just going to be hydrogen carbonate in equilibrium with the carbonate ions. So we've got the hydrogen carbonate in equilibrium with the carbonate ions, and obviously we're going to get a hydrogen ion in there to balance it. The Henderson-Hasselbalch equation can be used to find the pH of a buffer solution when the concentration of the acid and concentration of the conjugate base are known. And you can see pH equals the negative log of the acid dissociation constant plus the log of the concentrations of the conjugate base over the concentration of the acid. Some examples. Have a go at that. It really is just plugging some numbers in, see if you can do it. Okay, you can see that the equation will be used in biochemistry and medicinal chemistry options if you choose one of those. And the equation can be found in table 1 of the data booklet. We have 25 centimeter cubed of 0.1 mole of sodium hydroxide, strong base, is added to 50 centimeter cubed of 0.1 molar ethanoic acid, weak acid. So we've got half the amount of the strong base, which is what we want to make a buffer solution. So we know that half of the ethanoic acid is going to be form its conjugate base, the anion. So the conjugate base will equal the concentration of the conjugate base will equal the concentration of ethanoic acid, and so the pH is going to equal the pKa. So it's going to be 4.76 because it tells you that in the question. B, 5 grams of sodium ethanoate is added to 50 centimeter cubed of 0.1 mole decimeter cubed of ethanoic acid solution. We're going to assume no volume change occurs when the salt is added. First thing we need to do is find out the molar mass of sodium ethanoate, and do quick maths. You find it's 82.14 grams per mole. We've got 5 grams of the stuff, so we can use the molar mass to convert grams into moles. Do the maths there to get 6.09 times 10 to minus 3 moles. Next, we've got to find the concentration. We see it's 50 centimeters cubed we've got here, and so we need to include that. We're going to change it to decimeter cubed, so we're putting in 1000, the conversion factor. So we've got 0.122 moles per decimeter cubed. Now we can use our equation and plug those things in. We've got 0.122 for the ethanoic ion. We've got 0.1 moles for the ethanoic acid here. You just do the math and you get your answer. Splendid.